Hello student, last class we have discussed what is galvanometer and what is sensitivity of galvanometer. Clear? Now today we will discuss about what is emitter and what is voltmeter. You know, emitter and voltmeter is an instrument or electrical instrument which is used to measure or which is used to measure the flow of current through a circuit. And what is voltmeter? Voltmeter is also an electrical instrument which is measure voltage across the resistor, and emitter which is measure the current flowing through the circuit. So first, what is emitter? We know emitter is an electrical instrument which is always measure current, and this emitter which is always connected in series with the circuit. Suppose we have a circuit diagram. There is a resistor R and current flowing through the resistor is I. If you want to measure this amount of current, now we have to use a emitter in the circuit which is series with the resistance, which is series with the circuit. Clear? This is known as emitter. This is known as emitter. What is voltmeter? It is also an electrical instrument. Suppose we have a resistor R1, and there is another resistor R2, and current flowing through the circuit, that is I, and these two resistors are connected across a potential difference of V volt. If you want to find the potential difference across the resistor R2, so we have to use a voltmeter in the circuit, and that voltmeter always connected parallel, across that resistor. So this is voltmeter, and this voltmeter always connected in parallel with the resistance, where we have to find the potential difference across it. But emitter always connected in series with the circuit. Clear? Okay. So in this case, our aim to convert a galvanometer into emitter. How emitter can be converted from a galvanometer? How voltmeter can be converted from a galvanometer? First, we will go for conversion of emitter or galvanometer converted into emitter. Galvanometer converted into emitter. Galvanometer converted into emitter. Suppose first we will go for a circuit. Suppose we have a circuit. There is a resistor of resistance R equal to 5 ohm, and which connected across a potential difference of 10 volt. So current flowing through the circuit, that is 2 ampere, because I equal to V by R. So total potential difference or total EMF by total resistance, that is current, I equal to V by equal to 2 ampere current flowing through the circuit. This is mathematical calculation. That means if there is a 10 volt supply, if we use a 5 ohm resistor across the circuit, then what is the current of the circuit? In this case, the current flowing through the circuit is 2 ampere. How can we know the current flowing through the circuit is 2 ampere? Here we have to use a ammeter to determine this amount of current. Clear? Now, suppose we know ammeter which is always connected in series with the circuit. So if we want to determine this current, first we have to use a emitter. This is one emitter which is connected in series across a potential difference of V volt. Suppose this potential difference, that is 10 volt, and this resistor is 5 volt. But we have to find the current flowing through the circuit. But this is a mathematical expression, and current flowing through the circuit is 2 ampere. Here we have to find the current flowing through the circuit, how much, and the reading of the emitter. So this emitter, all the electrical appliance, all the electrical instrument which have a resistance. So emitter also has some resistance. Suppose the resistance of emitter which is equal to 5 ohm. Suppose then total resistance of the combination, then total equivalent resistance of the combination can be written as series connection. So 5 plus 5 equal to 10 ohm, and total voltage equal to 10 volt. Then current flowing through the circuit, or current read by the emitter, that is I equal to V by R. This 10 by 10 equal to 1 ampere. So this amount of current which shown by emitter, but actually this current was 2 ampere when there is no emitter. This is mathematical expression. But here if we use a emitter, then the current is 1 ampere. That means 50% current loss. 50% current loss. Clear? And this ammeter is known as bad ammeter because it losses 50% loss. It consumes 50% current. So this is bad ammeter. Now we have to determine how the reading of emitter which is very close to 2 ampere. How can we get the reading of emitter which is nearly equal to 2 ampere, not equal to 2 ampere, which is almost equal, or you can write 1.8 or 1.9 because here 2 ampere, 1.8 ampere, 1.9. This is also more emitter, but here we get only 1 ampere. So if we want to find the reading of emitter, that is 1.8 or 1.9 ampere. So what is the condition for which this emitter show the reading which is equal to 1.8 or 1.9 something? How? That means if the resistance condition, what is condition for gold emitter, the resistance of emitter tends to 0, not equal to 0. Tends to 0 means nearer to 0 but not equal to 0. And if resistance of the emitter tends to 0, then total resistance of the circuit which is nearly equal to 5. If resistance of the circuit which is nearly equal to 5, then current flowing through the circuit is 2 ampere. So for gold emitter, the resistance of the emitter should be 0, and for ideal emitter, that is add a resistance of the emitter should be equal to 0. This is tends to 0 for gold emitter. For ideal emitter, then R resistance of the emitter equal to 0. Clear? Okay. Now we have to construct, or we have to convert a galvanometer. We have to convert a emitter from galvanometer. Okay. This is circuit diagram. So this is resistance R. Suppose this resistance R, and current flowing through the circuit I. Suppose this current flowing through the circuit I. This is example. How to determine, how to use emitter. So this resistance or external resistance R, and we have to convert an emitter from galvanometer. Clear? So here we have to use a galvanometer. Suppose there is one galvanometer and resistance of the galvanometer we can write, it is Rg. Suppose Rg. What is Rg? Rg means resistance of the galvanometer Rg. Clear? Okay. Now the galvanometer show deflection for small amount of current. That is the meaning of galvanometer. That means it can measure a very small amount of current. Suppose this galvanometer and scale, here 0 reading, this is final scale, this is 0, 1, 2, 3, 4, or here final reading. If we apply 0.1 ampere current, then galvanometer shows full deflection. Suppose for 0.1 ampere current, if there is a circuit, if we use a galvanometer, if the current flowing the circuit that is 0.1 ampere, then it shows full deflection. If current flowing through the circuit that is 1 ampere, this is 0.1, if 1 ampere, then the galvanometer will be damaged because it can measure up to a full deflection when current flowing through the circuit that is 0.1 ampere. So if there is a current I flowing through the circuit, so the galvanometer only accept a small amount of current, that is this is small amount of current Ig. Suppose this amount of current which is 5 ampere and this is Ig with so full scale deflection, that is 0.1 ampere. The remaining current means 4.9 ampere current. We know if there is two branches, then the current can be divided, or the current can divide for parallel connection. So if there is another path or another way to flow of current, then if galvanometer permit or galvanometer allow 0.1 ampere current, then the remaining current can flow through this direction. And here we have to use a resistance, and the resistance is known as shunt resistance. This is the meaning of shunt resistance, and the value of shunt resistance is, and its value which is less than galvanometer constant Rg. That means Rg which is very greater than shunt resistance is. Why? If resistance decrease in the circuit, then current flowing through the circuit increase. So if S decrease, then maximum current can prefer to pass through this direction because resistance decrease. So here, if total current flowing through the circuit, that is I, then Ig current which is flowing or passes through the galvanometer, then rest current or remaining current which is passed through this shunt resistance, and its value very small as compared to galvanometer resistance. So here the remaining current is I minus Ig. I minus Ig. Clear? Okay. Now this combination, here this combination is known as emitter. This combination is known as emitter because we can find the effective resistance of this combination, because this is parallel combination. So we can write effective resistance or R equivalent this is emitter, so you can write resistance of emitter means total equivalent resistance, that is emitter. So total equivalent resistance, which is resistance of emitter, can be written in parallel combination 1 by Rg plus 1 by S. Clear? So this is for board emitter, that means Ra tends to 0. What is the condition? Because we cannot change the value of Rg. This is fixed for a galvanometer, but we can change shunt resistance. We can change shunt resistance. If we decrease the value of shunt resistance, suppose this is equal to 0. If we decrease the shunt resistance up to 0, it is very small resistance, then this factor 1 by 0, which is equal to infinite. That means 1 by Rg plus infinite plus something which is equal to infinite. So here 1 by Ra, which is equal to infinite. That means 1 by 0, which is equal to infinite. That means Ra tends to 0. Or Ra equal to 0. That means here for conversion of emitter, we have to use a shunt resistance whose value is very small, and that shunt resistance always connected parallel with galvanometer. Clear? And the value of shunt resistance is very small, and this is the formation of a emitter from galvanometer. Clear? So this is the condition for galvanometer. Sorry, emitter. How to determine emitter from galvanometer? Clear? So for board emitter, Ra should be 0 or tends to 0. For ideal emitter, Ra equal to 0. You have to remember this relation. Clear? Okay. From this relation or from this diagram, we can write this is total current I. Here current flowing through Ig. Here current flowing through I minus Ig. Shunt resistance S. This is Rg. What is Rg? Rg means galvanometer resistance. Okay. There is 2 point A and point B. The potential difference across 2 point A and B, which is constant, because this is parallel connection. Here potential difference and this potential difference is equal to constant. So we can write potential difference that is equal to Ig, that is AB. Potential difference across AB, which is equal to Ig into resistance, Ig into Rg, which is equal to here current I minus Ig, which is into S, or you can calculate shunt resistance, that is equal to S equal to Ig Rg divided by I minus Ig. You have to remember this relation. What is Ig? The current which is passed through the galvanometer. What is Rg? Resistance of the galvanometer. What is I? Total current flowing through the circuit. So in this way we can calculate the shunt resistance. Clear? Here you have to note this point. For board emitter, Ra tends to 0. For ideal emitter, Ra equal to 0. Clear? Okay, this is all about the conversion of emitter from galvanometer. But in this case, we can calculate the effective resistance also. So, in this case, the effective resistance can be calculated. This circuit, this resistance Rg, and here one shunt resistance, that is S. So this parallel connection, so effective resistance can be write R equivalent equal to 1 by Rg plus 1 by S, or 1 by Rg equal to, that is Rgs divided by Rg plus S, or sorry, this is R equivalent, which is resistance of emitter. Equivalent means resistance of emitter, which can be write, that is R equal to R G RG S divided by RG plus S. This is equivalent resistance or resistance of emitter. Clear? So this is the mathematical formula to determination of resistance of emitter, which is in terms of resistance of galvanometer and shunt resistance. Now we have to discuss, or we have to convert a galvanometer which can be converted into voltmeter. Galvanometer converted into voltmeter, or a voltmeter can be converted from galvanometer. So you know, voltmeter always connected in parallel across the circuit. Suppose one example. Suppose we have two resistors. This resistance R equal to 6 ohm and another resistor R equal to 6 ohm. Connect across a potential difference of 24 volts. Suppose 24 volts. Clear? Now the potential difference across 6 ohm resistor, that is 12 volt, and another 6 ohm resistor also, that is 12 volt. This is mathematical expression to determination of potential drop across this resistor and this resistor. Clear? Now if we use, this is 6 ohm resistor and this is 6 ohm resistor, and across a potential difference of 24 volt. So we have to find, or we have to determine the potential drop across 6 ohm resistor by using a voltmeter, and you know, voltmeter always connected across the resistance which is parallel. Clear? Voltmeter always connected across resistor is parallel. So this is voltmeter and this is 6 ohm resistor. Suppose this voltmeter, because all electrical instrument which has a definite resistance, suppose this voltmeter consists 3 ohm or 2 ohm or any resistance, suppose 6 ohm resistance, 6 ohm resistance. Now total resistance of the circuit you have to calculate, that is R equivalent equal to, this is 6 plus 6 3 is, you know, 6 3 18 by 6 3 9, that is 2. So 6 2, that is 8, that means R equivalent 8. So current flowing through the circuit I equal to total EMF, that is 24 by total resistance 8, that is 3. Clear? So total current flowing through the circuit is 3 ampere. If 3 ampere current flowing through the circuit, then here the fast resistor drop a potential difference across it, that is 3 into 6, the 18 volt. Clear? Which is initially drop, that is 12 volt. Now after use a voltmeter whose resistance is 3 ohm, then the 6 ohm resistor, initially 6 ohm resistor drop 12 volt potential difference. Now this resistor drops or consume 12 volt potential. The remaining potential, because total potential 24, here 6 volt. Clear? That means initially the potential across second resistor 12 volt, after connects through a galvanometer. If we connect galvanometer of resistance 3 ohm, then potential across the resistor of second resistor, which is 6 ohm. That means 50% loss. Because this voltmeter is bad voltmeter. This voltmeter is a bad voltmeter. So how can we change the resistance of voltmeter so that the potential measured across the 6 ohm resistor which is nearly equal to 12 volt, or it may be 11.9 or 11.8 volt. So what is the condition or what is the resistance of this voltmeter such that the voltage drop across the second resistor initially which was 12 volt. Now what is the condition for which this second resistor drop a current which is nearly equal to 12 volt, and the reading of voltmeter which show nearly equal to 12 volt or 11.9 volt or 11.8 volt, and that is known as, and this is a good voltmeter because its reading which is approximately equal to initial reading which was mathematical reading of 12 volt. Clear? So we have to increase or decrease the resistance of voltmeter so that we get the approximate value or exact value of the initial stress. So in this case we have to increase. If we increase the resistance, because voltmeter connected across the second resistor is parallel. If we increase the resistance of voltmeter, suppose we increase the voltmeter resistance, that is suppose 12 ohm. Increase 12 ohm, or here you can write. Suppose this voltmeter resistance equal to 12 volt and this terminal is 6 volt. Clear? Okay. Total resistance, this can be right, it is 6 ja 72 divided by 18 which is equal to 4. Clear? So equivalent resistance here 4 and here 6. 6 plus 4 which is equal to 10. So R equivalent equal to 10 ohm. Then here 24 volt supply. Then current can be write I equal to 24 by 10. So which is equal to 2.4 ampere. That means here current will initially current 3 ampere when resistance 3 ohm. When resistance of the voltmeter equal to 12 ohm, then current will through the circuit, that is 2.4 ohm. And for 2.4 ohm, here 6 ohm resistor. So it drop a potential, and this potential can be right, and this potential which is equal to V equal to IR, which is equal to V, I means 2.4 into 6. Clear? Or this potential drop can be right, that is 2.4 into 6 or 24 by 10 into 6, 5, 3. Clear? So which is equal to 24 into 3, 72 by 5. Then 5 1 5, then here 2, then 5 4, then it drop 14, then almost nearly equal to, it drop 14, then remaining is will drop 10. So which is nearer to 12 volt, because we get 12 volt as a 10 volt after using a voltmeter whose resistance is 12 ohm, which is nearly equal to the initial value. So from this example we conclude that the resistance of a voltmeter which connect across a resistor with parallel, and its resistance must be high, so that we get the actual voltage drop across the resistor. Clear? So from this example we conclude that for a good voltmeter, the resistance of voltmeter tends to infinite. not infinite, tends to infinite. Second thing, for an ideal voltmeter, resistance of voltmeter should be equal to infinite. This is important case because for this resistance we get the actual potential drop across the resistor. So here we have to draw a circuit diagram. Suppose this is resistor R, external resistor, and current flowing through the circuit I. Clear? And there is a galvanometer whose resistance Rg. Now we have to increase the resistance of a voltmeter. So here we have to use a high resistance, or you can write that is S. Clear? So we have to use a high resistance, but in series connection, this is galvanometer. In series connection, the equivalent resistance can be write, that is R equivalent equal to Rg plus S. Rg plus S. But this is equivalent resistance, and if this equivalent resistance will be infinite, then this total setup is known as voltmeter. So for construction of a voltmeter from galvanometer, we have to use a high resistance with series connection. We have to use a high resistance with galvanometer. So this resistance is very high. If this resistance is infinite, because this is constant quantity. Because why? Because this is the resistance of galvanometer. If we increase this resistance, then this resistance also increase. So R equivalent can be write resistance of voltmeter, which is equal to Rg plus S. This is also known as shunt. This is all clear. Okay. So in this case, this is voltmeter. Suppose current flowing through the circuit is I, and the total current here. Suppose if you connect a potential this terminal, that is V, and current flowing through I, and here total current flowing, because we have to remember first condition, this is resistance R1 and this is second resistance R2, where potential difference V volt, this is R2, but here we have to use a voltmeter. Clear? So we have, or we can write that is, to make a clear diagram for better understanding. This resistance R, this we have to determine the potential drop across this resistor R2. So this resistor R2, clear? Okay. This is R1, this resistor R2. Now we have to use here this is voltmeter. So conversion of voltmeter, that is a galvanometer with resistance Rg, which is equal to, and the connected with a shunt resistance, very high resistance, which is series connection with the galvanometer. Suppose the total current flowing through the circuit I, because here total current flowing through the circuit I, the circuit is potential V. So total current flowing through the circuit I, but here only Ig current flowing through the circuit, and The remaining potential here can be write, that is I minus Ig. Clear? So here I minus Ig equal to R2, and this setup, this total setup is known as voltmeter. Clear? Suppose the voltmeter will show the potential, that is V. If we make a simple circuit diagram to understand the conversion of voltmeter, that is, we can draw this diagram. There is a galvanometer G whose resistance Rg, and we connect a shunt high resistance with series, and this total term is known as voltmeter. Clear? A potential drop and potential show across the voltmeter is V, and current flowing through Ig. Ig current flowing through this point is Ig, current flowing through the voltmeter. So you can write this potential which is equal to current into total resistance, that is G, resistance of galvanometer, shunt resistance is. Clear? So you can write this resistance, high resistance, or V equal to Ig Rg plus Ig into S, or Ig into S, which is equal to V minus Ig Rg, or S equal to V minus Ig Rg by Ig. Or you can also write this shunt resistance or high resistance, that is S equal to V by Ig minus Ig by Rg, that is equal to Rg. Clear? Okay. So this is the mathematical formula. The high resistance is value very clear. Okay. And you can determine the high resistance by using this relation. Clear? Okay. Now we will go for effective resistance. Effective resistance of a voltmeter. Effective resistance, because in series connection we can write total equivalent resistance equal to Rg plus S. Clear? And this total setup is known as voltmeter, so R equivalent is known as resistance of voltmeter. Here S is very large as compared to Rg. Clear? So for good voltmeter, that is the value of S tends to infinite. For ideal voltmeter, the value of S is equal to infinite. You have to remember this relation. For emitter, the shunt resistance always connected parallel, and this shunt resistance is very less as compared to galvanometer resistance. If resistance of the circuit is 0, then the emitter is known as ideal emitter. But in case of voltmeter, the shunt resistance or high resistance, which is always connected parallel with the resistance connected parallel with the galvanometer, and the value of shunt resistance which is very high as compared to the resistance of galvanometer. Clear? if for a gold voltmeter, if the value of some resistance which tends to infinite, then the voltmeter can be treated as gold voltmeter. If some resistance, the value of some resistance which is infinite, very large value, then the voltmeter is known as ideal voltmeter. Clear? This is all about the conversion of emitter and